Hi, folks. For solution mixtures, the use of molarity to quantify the concentrations of solutes and solvents is the favorite unit of chemists. It serves as the most direct link between the volume of solution to moles of the solute. But there are other concentration units that chemists use. And in this lecture, we will focus on a couple of these quantities. We also will look at a lab method in computation that occurs quite frequently in chemistry, a dilution.
Molarity values are not necessarily the most rigorous and accurate concentration unit available to chemists. The density of a solution is temperature dependent, with volumes usually increasing as temperature increases. Now, if the temperature changes, the total volume of solution changes, and the molarities will be altered because the molarity is defined to be the moles of solute divided by the total volume of the solution. But now the total volume is changed. Now, it'd be nice to have a concentration measurement that doesn't suffer from this temperature malady, yet still is based on the chemist's love for moles. The concentration measurement we use if we want something more constant with temperature changes is the concentration unit called a molality. This molality unit symbol is a small letter m. The measurement of molality takes the total moles of a component in the solution divided by the mass in kilograms of just the solvent. Note, this is a mass of the solvent, not the mass of the solution. So for every kilogram of the solvent, the molality is the number of moles of the component we will have. The problem is solved, right? The number of moles of the component and the mass of the solvent are both temperature independent. So a molality value will not change with a sudden temperature variation. So why isn't this type of concentration unit used more often? Again, when using molarities, it is so easy to think about measuring out a certain number of moles of a compound by simply measuring out a volume of a solution and doing one simple computation using molarity values. Using molalities is not as straightforward. Let me describe how we use molalities to measure out a certain number of moles of a component. We first divide the moles of the chemical component we need by the molality to figure out the mass of the solvent, not solution. We also would take the moles desired and convert it to the mass of the component using the molar mass of the compound. We add the mass of the chemical and the solvent together to get a mass of the solution. Now we weigh the required amount of solution out on a balance. We can use volumetric glassware, but we will need to know or measure the density of the solution at the current temperature if we want to do that. Whew. See, the use of molalities comes with a price. But no worries, we won't concern ourselves with using molalities very often since molarities are usually good enough for most benchtop chemistry. But remember, a molality unit is a more accurate and robust value than a molarity unit. Another reason to remember molalities is that for some measurements, it is the required concentration unit. For physical processes like colligative properties, things like freezing point depressions and boiling point elevations of solvents, we have to do the computations using molality units. Let's look at another concentration measurement, a mass percent. A mass percent also does not change with temperature changes. This concentration unit is straightforward to measure and calculate, but not used as often by chemists because, like molalities, you need to do an extra calculation to get to moles of a component, and we're relying on masses rather than volumes. Chemists can be a lazy lot, and we try to do as little math as possible. So, let's look at describing a concentration of a solution by mass percent. Now, the units of mass percent are, well, there really aren't any units, but a mass percent is the total mass of the solute component divided by the total mass of the solution times 100. Another way to think about this mass percent is that the mass percent is the number of grams of the component if we had 100 grams of solution. So, if the mass percent of ethanol in water is 6%, let's say, I like to think that if I had 100 grams of this solution, then I would have 6 grams of ethanol. We can use a balance to measure the proper amount of solution, or if we also know the density of the solution, it's a simple matter to turn the mass of a solution into a volume of the solution, and now we can use our volumetric glassware again. So let's do a problem. The mass percent of sugar in a can of aqueous sugar solution is 16.1% sugar and has a density of 1.062 grams per ml. What will be the volume in milliliters of a can of this solution if I know there are 26.0 grams of sugar in this can of sugar water? Now, this is the amount of sugar that's typical in a can of soda. So let's produce the solution map for this problem. The end of the map is the thing we want, the volume of the solution in the can, and the beginning will be the given information, 26.0 grams of sugar. The solution map goes as follows: grams of sugar to grams of solution, using the mass percent, to the volume of solution, using the density or trusty gram per milliliter connector. Now we use the mass percent to convert the grams of sugar to grams of solution, knowing that for every 100 grams of the solution, there are 16.1 grams of sugar. We then know from the density that for every milliliter of the solution, it weighs 1.062 grams. So in the end, we obtain a final volume of 152 milliliters of solution. To finish things up, I want to talk about a common lab practice that we often do in chemistry. We will buy often very concentrated solutions of a chemical, such as 12 molar hydrochloric acid or 19 molar sodium hydroxide. But we don't usually use these dangerous chemicals at these caustic concentrations. We often dilute the chemicals with more water or solvent to make solutions with lower molarities. At water treatment plants, they may find they have a dangerous chemical like lead in the drinking water at concentrations that are not acceptable. Now, it may be too costly to get the lead out chemically, and the chemicals they would use might be just as bad as the lead itself. A better alternative may be to simply dilute the polluted water until the lead concentrations are no longer a threat to public health. So, the common question goes something like this: how many milliliters of concentrated 11.65 molar hydrochloric acid do I need to make 250 milliliters of a diluted 2.5 molar HCl solution? The equation we use to do dilution problems is M1V1 equals M2V2, where M1 is the molarity of the concentrated solution, and V1 is the volume of this solution, the value we want to find. M2 is the molarity of the diluted solution, and V2 is the volume of this solution. First, look carefully at the product M times V. Let's say the volume is in liters. We know that the molarity has the units of moles divided by liters, so the product cancels the volume and we're left with moles. The idea is that the number of moles we deliver from the concentrated solution remains the same when we dilute the system with more solvent. We don't change the moles of solute when we dilute it. That makes sense. Second, it doesn't matter what units we use for the volumes in this simple equation, because ultimately we are dealing with simple ratios. With very little algebra, I can rewrite the equation as M1 divided by M2 equals V2 divided by V1. We now can see that units in the volume ratio cancel if the volume units are the same. The same goes for the concentrations for the most part. Only the numbers remain. So V1 and V2 can be milliliters or liters just as long as we are consistent and use the same volume units for both V1 and V2. So now it's time to solve the problem. We want to solve for V1, the volume of the concentrated solution. We use algebra to solve for this variable and get the equation V1 equals M2V2 divided by M1. M1 is 11.65 molar, M2 is 2.5 molar, and V2 is 250 mils. We plug in the values and calculate a value of 53.65 mils, which we must round off to 54 mils since M2 has the least number of sig figs. In practice, we would take a 250 ml volumetric flask, which is nothing but a very accurate and precise volume container that has a line on it that denotes when we have 250 mils in the flask. We would fill it half to 2/3 full of water. We would use a burette or pipette to measure out 54 milliliters of concentrated HCl acid carefully and deliver it into the volumetric flask. Warning: we always pour concentrated solutions into less concentrated solutions. So if we delivered the concentrated HCl to the volumetric flask first and then poured water into this HCl solution to dilute it, we would generate a bunch of heat and worse, HCl vapors. That would be bad. Continuing, once we put the 54 mils of concentrated solution into the flask, we would swirl the volumetric flask to help mix the solution a bit. We then fill the flask to the 250 milliliter mark with more water. And we finish by capping the flask and inverting it 10 to 15 times to make sure the solution is thoroughly mixed. And now we have 250 mils of a 2.5 molar HCl solution.
Okay, this series of lectures highlighted very practical knowledge required in almost every science laboratory in the world. Be sure and spend time with this series of lectures and do plenty of practice problems. Your ability to do these computations are worth having in your toolbox. Catch you later.